So, we were discussing about canonical forms, that is to reduce second order linear partial differential equation into another second order linear partial differential equation with the change of variables from xy to xi eta variables, where xi and eta are functions of xy. We have seen if the discriminant is non-zero, we reduce that equation into canonical form of either a special form like mixed derivatives u xi eta plus lower order terms is 0. So, that is either hyperbolic or parabolic. We will see what happens if b square minus 4 is there when the discriminant is 0, what happens. So, we will get another canonical form. So, we will see that in this video. So, we will just look at the equation when b square minus 4ac is actually equal to 0. So, you get this one. So, what we have seen is this this equation, the general second order equation becomes this equation. This is what we have seen with this a star, b star, c star, and you have the transformation is such that this Jacobian of what j means, Jacobian of xi and eta. Okay, so that is what is a function of x as a function of xy. Okay, so this is, we also wrote j. So, both are same. So, j is actually j of xi eta, that is xi x xi y, eta x eta y. This is non-zero. Okay. Okay, so this is what is non-zero, and your equation, original equation is a u x x plus b u x y plus c u y y plus d u x. So, you can say lower order terms. Okay, lower order terms equal to 0. So, this is what you have, is the original equation that we reduced into this kind of second order equation. So, how do I fix my xi and eta? So, the best way to do this, to fix this, to find this xi and eta is to choose a star equal to 0 and b, c star equal to 0. So, let us start with a star equal to 0. Let us make a star equal to 0. So, by choose a star equal to 0. So, can I fix my transformation variable xi of xy. Okay, so that is why we are choosing. So, a star is what is the a star? A is xi x square plus b xi x xi y plus c xi y square equal to 0. So, if I choose this, I know a, b, c given from the given equation. So, if I substitute and you make it is equal to 0, a star equal to 0. So, what you do is, suppose a is 0, okay, and if a is 0, I can choose, I assume that a is without loss of generality, I assume that a is non-zero. Okay. So, without loss of generality, assume that a equal to 0. If a equal to 0, okay, so I can write c xi y square plus b xi x xi y equal to 0. Okay. If a actually a equal to 0, okay, assume that a is non-zero. Without loss of generality, you can assume that a is non-zero. If a is 0, this is what it becomes. Okay. So, the idea is I divide, so that I can divide xi y both sides, xi y square both sides, okay, or rather xi x you divide, xi x square if you divide both sides, then become this becomes xi y. Okay, so you get like this. If your equation, if a is 0, your equation becomes this is how you write it. If c is also 0, then what happens? Your equation becomes xi x xi y equal to 0. Okay. So, and we know that b cannot be 0. If b is 0, that means everything is, there is no second order differential equation. So, b, if a and c both are 0, it is already in the form of canonical form. Okay. That is one of the canonical form, it is already there. So, b should be non-zero, and clearly b square minus 4ac in that case is always positive, it is elliptic. hyperbolic that is actually already in the normal form wave type. Okay. So, we will see that. So, your aim is to make this terms without having uxx and uyy terms, you want to make it 0 after transformation to xi and eta. That means you choose your a star and c star 0. Okay. So, first I make it a star equal to 0. So, you know a b c, if a is non-zero, you can always assume that a is non-zero. If a is 0, c should be non-zero. Okay. If c is also 0, that means it is already in the canonical form, already in the standard form, one of the standard forms, hyperbolic form. Okay. So we are so we can assume that a is non-zero and c is also non-zero, you can assume. So, if c is 0, c can be 0. Okay. So, you have this one. Now, you divide with xi y square both sides. So, if we do that, xi x by xi y whole square plus b xi x by xi y, okay, plus c equal to 0. This is what you have if a is non-zero, that is what we assumed. So, you have this. If a is 0 and c is non-zero, you work with this. So, you divide with xi x square. So, you have, so in this case if a is 0, so what you have is c times xi y by xi x whole square plus b xi y by xi x equal to 0. Okay. This is what this is the equation you work with. So, you have this one when a is not equal to 0. Now, what is that we are doing actually? So, you are taking these x y variables into transform to xi eta variables. Xi eta variables are, this is your xi and this is your eta. Okay. This kind of variable. So, xi, so any point x y belongs to these two lines. This point is here x y. So, this straight lines intersection. So, that means here also it belongs to that x y point belongs to, corresponds to it, when you do this it will become xi y. So, it will be some other point here. So, that will be parallel to this this one. This is actually equal to xi equal to some constant c1, eta equal to some constant c2. So, that is the point, this is your xi and eta. Okay. So, we are interested only because we have chosen a star equal to 0, I have this involves only xi. So, when you transform from here this domain to that domain, any point x y becomes a point in xi eta that is actually passing through this curve xi equal to some constant. So, that means you can have xi of x y equal to constant c1. Okay. Now, what is the total derivative? D xi equal to 0. So, what is the total derivative of this means? This means xi x dx plus xi y dy equal to 0. So, this implies, but what we need is xi x by xi y. So, xi x by xi y equal to minus dy by dx. So, this you go and replace there. So, this if you put it here, so you can see that if a star equal to 0, assuming that a is non-zero, so you have dy by dx whole square minus b dy by dx plus c equal to 0. So, this is what you get. Okay. So, now I can find what is my dy by dx. Okay. From this is the quadratic equation in dy by dx. So, you can calculate the dy by dx. Okay. So, dy by dx equal to b plus or minus square root of b square minus 4ac divided by 2a. So, this is what is your equation. So, this is the differential equations. These are two ordinary differential equations. If you solve them, you get your xi and eta. Okay. So, you can get, if you just try to solve this, you get your xi. Okay. So, okay, first we see that this is what you get. If you work with same thing with if you choose b star equal to 0, rather C star equal to 0. You choose now C star equal to 0, and if you choose if you assume that in this case A is non-zero, so what it becomes, if C star equal to 0, if C star equal to 0, okay, then what you get is A times eta x by eta y whole square plus B times eta x by eta y plus C equal to 0. Okay. So again, if you replace, again see, this is also not true. So if any point x y to xi and eta, xi is constant, and also eta belongs to, so eta of x y equal to C2. So not only this, you have eta of x y equal to C2. Again you have the same thing, b eta equal to 0, total derivative. So that means eta x dx plus eta y dy equal to 0. So what does it mean? So this implies you get eta x by eta y is minus dy by dx. So if you substitute here, you get the same thing. So what you get is, you finally get the same thing. So in both the cases, you try to substitute this here, what you get is this only. So in both, for xi and eta, if you make A star and C star equal to 0, what you end up is two ordinary differential equations, these two. Okay. So one is dy by dx equal to b plus or minus square root of b square minus 4ac by 2a, and other one is dy by dx equal to b minus square root of b square minus 4ac by 2a. These two are two different ODEs if b square minus 4ac is non-zero. Okay. So we can observe that if b square minus 4ac is non-zero, then I have two ODEs. The above ODEs are distinct, they are different. Okay. So you solve them. If you solve them, what you get? So try to assume that this is simply, you try to solve them, what you end up is some function of x y equal to constant. Okay. This is actually what you get is y equal to integral, and b and a c, these are functions of x y. So you have dy by dx equal to functions of x y. So this is a ODE, as such you can solve it. So if you solve it, some what you get is, say, let us call this xi of x y equal to constant. Okay. This is your C1, and this one you try to solve again with this. This if you solve, you end up finally another arbitrary constant C2 is what you get. So you can get your, by solving these two ODEs, you get a general solution as xi of x y, you call it xi of x y. Okay. That is your xi, and this is your eta, that is your eta variable. Okay. So if you solve this ODE, you let us say you call some f1 of x y equal to constant, and that is your xi, you take it as your xi, and you do say for example f2 of x y equal to constant after solving this ODE, and once you get that, you take that variable eta as this your f2. Okay. So I myself is calling here xi itself. After solving this, you get some function of x y that I am calling xi of x y, that is my new variable xi. Now I have xi of x y equal to whatever xi is equal to some combination of x y. Similarly, when you solve this one, which is I myself is calling, here I am defining as eta of x y equal to C2 as a general solution. So that is, so whatever the combination of x y is my new variable eta. Okay. So those are your curves actually, those are your basic curves. So whatever you solve these ODEs, they are nothing but the solution curves of those ODEs are nothing but these curves here after transformation, because you started with those, from them you derived. Okay. So with this, now you know what exactly those xi and eta from these two ODEs. So if you are given a second order partial differential equation, linear partial differential equation with A, B, C, you start with these two ODEs, get get your two curves xi and eta. Once you know xi and eta, you simply use the change of variables which I have done in the last video and get your form, okay, get your form that is here, in which how I derived my xi and eta and I made that A star and C star are 0. So what you get is B star u xi eta plus lower order terms will be 0. What you end up will be B star u xi eta, because A star and C star I have chosen to be 0, plus lower order terms equal to 0. So this is the canonical form you are looking for, okay. This is the hyperbolic case, okay. This is the canonical form, either hyperbolic or elliptic, because I have chosen only that it is non-zero, okay. If it is positive, you call this canonical form is hyperbolic form. If it is negative, you call this elliptic form, okay. What you get is, in that case if it is negative, what you end up is your xi xy will be complex function, okay. Similarly eta xy will be complex function if b square minus this discriminant b square minus 4ac is negative. If it is positive, you have a real root, so there will not be any imaginary number I if it is positive. So what you end up after integrating this ODE, you have a real valued function xi xy, okay. So you have a xi xy, that is real valued function xi. So xi and eta variables will be real variable real functions of xy if b square minus 4ac is positive. In that case what you get is u xi eta are real variables, real functions. So in that case it is a hyperbolic equation, okay. If they are negative, b square minus 4ac are negative, xi and eta will be complex functions. So in terms of those complex functions, if you write u complex functions xi and eta, okay. So if it is complex, what you end up with these two will be same except that one is taking the bar, okay. So what you end up is eta will be xi bar, okay, eta will be xi bar. So xi bar, when xi and eta are complex functions and b square minus 4ac is negative, and that is the elliptic form, okay. So these are actually same, so we can derive from this when by considering b square minus 4ac is non-zero, okay. We will see with examples when this is non-zero, okay. So this is how you get with so what you got is your xi and eta variables if b square minus 4ac is non-zero, okay. So canonical form either that is hyperbolic or elliptic. This is the canonical. If you have in this form, if xi and eta are real, that is hyperbolic. If xi and eta are complex functions, then it is elliptic if it is in this form, okay. And there is a question here, we have a b star. What happens to b star? B star, can it be 0? Question, okay. B star can be 0. If b star is 0, there is nothing, okay. So you have to make sure that b star is non-zero, then only you have in the canonical form. So how do you know that b star is actually non-zero? So answer is b star is actually non-zero. So this you can see from this one, b star square minus 4a star c star. This is the discriminant of transformed equation equal to, you can actually observe, you know a star, b star, c star from these three expressions, okay. You have these three expressions a star, b star, c star, okay, and you know a, b, c. So you here right hand side you have b square minus 4ac. There is a relation between this b square minus this discriminant and this discriminant, there is a relation. So they are related with this one. So j, that is the determinant of xi x xi y eta x eta y square. So this you can directly by putting a, b, c and a star, b star, c star and j, you know, you just substitute and you can see that this, you can verify that this equality is valid, okay. This actually, this equality is true. You can verify that just by substituting a, b, c and a star, b star, c star and j here, okay. So one can see, one can verify that, Now how do I know? From this I can show that B star is non-zero. Now I have chosen A star C star is 0, so you have this equality becomes B star square is actually J, that is non-zero square, and B square minus 4AC is non-zero. So this means this is non-zero. Okay, implies B star is actually non-zero. So you have this canonical form actually exists with B star, that is non-zero. Okay, so that can be either hyperbolic or elliptic. What happens if B square minus 4AC is equal to 0 in this ODE? If you take this B square minus 4AC, the two ODEs becomes single ODE. Either you consider A star equal to 0 or C star equal to 0. Okay, both will give you same only one ODE. Okay, so you will get only dy by dx equal to B square B by 2a, only B by 2a you get one ODE. Okay, assume, so you integrate, so you get your general solution as xi y equal to C1, that you call it one variable xi. Now eta, so you do not know how to find other variable eta to get the transformation. So now in this case when B square minus 4AC you get only one variable xi, eta is you can always choose. Okay, eta can be chosen any function of x y, x and y, or x or y or x and y both. Okay, such that the condition is a Jacobian of the Jacobian is xi x xi y, that is from here eta x, that is what you have chosen, eta should not be 0. Make sure that you choose some eta such a way that this Jacobian is non-zero. If you do that, that works. So with those are the two variables xi and eta. With those two variables you can reduce, you can go and reduce your given second order partial differential equation into a canonical form. How do we do this? In this case we have chosen A star is 0. Okay, so in both cases so again use the look at this equality. If B square minus 4AC is 0, then B star square minus and J is non-zero. So in any case write this B star square minus 4A star C star equal to 0, in which I have chosen A star equal to 0. Okay, A star already by choosing, how I got this ODE, I have chosen A star equal to 0. Okay, choose A star equal to 0, I get this ODE, one ODE. If you choose C star is also 0, you get a same ODE. Okay, so it is like assume that you have chosen A star equal to 0, I got this one ODE. Now you choose eta such a way that if you choose E star in such a way that Jacobian is non-zero, so unless this xi is actually, this eta is actually not same as xi, you will not see that C star will be 0. Okay, if C star is 0 means eta what you have chosen itself is xi, that means the Jacobian is actually 0. Okay, so if what is the Jacobian, if xi eta is actually same as xi, if C star is also 0, what you end up is the same ODE. If you integrate you get eta, you can integrate, so this will give you the same integration. Okay, so eta equal to xi of xy, so eta is the same as xi, so xi x xi y, eta is also xi, so xi x xi y, that means it is 0. So this condition is not satisfied, so you cannot just go to new variables so that you can come back. Okay, this will be useless. So if you choose A star equal to 0, C star is, so the moment you say that it is chosen in a function such a way that Jacobian is non-zero, immediately tells you that C star is non-zero. Okay, so C star is non-zero and A star is 0 implies B star square equal to 0. Okay, that implies B star equal to 0. So, what you end up, so final equation becomes A star is 0, B star is 0. So, you have C star which is non-zero U eta eta plus lower order terms equal to 0. So, if the discriminant is 0, we can have we can see that B star is 0. So, in this case C star is non-zero. So, that makes it you have C star U eta eta plus lower order terms equal to 0. So, this is what second order linear partial differential equation in the variables x and y you reduced into some C star which is non-zero U eta eta plus lower order terms equal to 0 in the case of discriminant B square minus 4AC equal to 0. So, this is called a canonical form. So, this is the form it becomes after transformation from xy variables to xi and eta variables. When the discriminant is 0, B square minus 4AC is 0, we can reduce the second order equation into this form. So, this is also called canonical form or normal form. Okay, we call this normal form. When B square minus 4AC equal to 0. So, this is how you are reducing. So, when you reduce this is you can see that this is actually this is something similar to parabolic equation, we will see what it is, or heat equation. Okay. And in this case this kind of form is called parabolic form, parabolic equation, this is similar to parabolic equation or heat equation. So, when the discriminant is non-zero, so this is how you can see the canonical form. So, the transformed equation becomes of this type. This is called a canonical form, that is either hyperbolic or elliptic depending on what kind of variables you have. If your variables xi and eta new variables are real variables, real functions of x and y, then it is called hyperbolic. If it is complex functions, xi and eta are complex functions of x and y, then it is called the canonical form is actually elliptic. If then the discriminant is 0, B square minus 4AC is 0. So, you see that the equation can be reduced after transforming the variables from xy to xi and eta, it becomes this type. This is the canonical form or normal form. This is called a parabolic equation, parabolic form, okay, when this discriminant is 0. So, this is how we reduce. So, after transforming the variables xy to xi and eta, so you can change depending on the discriminant value. If it is 0, you get a canonical form like this. Okay, you have to reduce into this type. If it is non-zero, you have to reduce into the earlier form u xi eta. Mixed derivatives, if you see, that is a canonical form for hyperbolic or elliptic, and if it is same variables u xi xi or u eta eta, then it is parabolic form. So, that is how it is. We will see exactly what happens when you consider discriminant is non-zero. What is the meaning of hyperbolic and parabolic thing? Okay. So, you just go back. So, if let us go back to when discriminant B square minus 4AC is non-zero. In this case, you have xi of xy and eta of xy, two new things as your xi and eta. So, these are your variables. In these variables, what you got is B star into u xi eta plus lower order terms equal to 0. So, this implies, since we have seen that B star is non-zero, so you have u xi eta plus you can divide it. So, you have it's again, so you can divide it. If you divide it, so it will be absorbed into the lower order terms equal to 0. So, this is what is if xi and eta are real valued function, that is what we said, it is a hyperbolic equation. Hyperbolic means is something similar to the waves. So, it has a different characteristics. So, what are the characteristics? If you see the characteristics of this equation is this has a wave solutions, that means the propagation waves, you can see that waves have waves propagate with a finite speed. So, it will have a finite speed of propagation. The solution will have you can see that you have a propagating kind of solutions with a finite speed. Okay. So, we will see that how it is. Once you get this xi and eta, So, what you do is you start with the new variables, some alpha alpha xi eta, okay. You call this in terms of alpha xi eta, alpha as xi plus eta, and xi and eta are real valued functions, and you call this beta xi minus eta. You take like this, take the sum and difference when xi and eta are real valued functions, real valued functions. So, this is one canonical form, hyperbolic form, when these are real valued function. So, if you change to one new more variables, what happens here when you do this? Alpha xi, beta xi, alpha xi, alpha eta, these are the new variables. Think of xy as the xi and eta, and xi eta as alpha and b, new transformation. This is the new transformation. So, with this new transformation you can see that Jacobian will be alpha xi alpha eta, beta xi beta eta. So, what is this one? This is actually 1 1 1 minus 1, and clearly this is non-zero. Since this Jacobian is non-zero, we can have the transformation. So, the equation becomes, so what you need? What you need is, you need to calculate u xi eta. U xi eta is do xi do eta of u. So, this you need do xi and do eta. So, how do I calculate do xi and do eta? Do u by do xi is actually, you can write do u by do alpha and d alpha by, or do alpha by do xi plus do u by do beta, because u is a function of xi and eta now, okay. So, here u is a function of xi and eta, and now xi and eta, because Jacobian is non-zero, you can actually get xi in terms of alpha beta. Xi is xi in terms of alpha beta, okay. So, it is like x in terms of x of xi and eta implies, okay. Since this is this, we can have eta xi eta in terms of eta alpha beta. So, you can just solve one in terms of, you can go back to the variables xi eta to alpha beta, and then you can come back from alpha beta to xi eta. So, that is why the transformation is invertible. So, you can see that this derivative do u by do xi I can rewrite like this, and do beta by do alpha. So, do beta, right, do xi, sorry, so do xi. So, this is what you have. So, now I know do alpha by do xi, what is alpha? Alpha is here. So, do alpha by do xi is 1. So, that is alpha xi is 1. So, that becomes do u by do alpha, do u by do beta, do beta by do xi is also 1. So, you have do u by do beta. So, do xi is actually is this. Similarly, and you can get do u by do beta, do eta, which is do u by do alpha, do u by do alpha into do alpha by do eta plus do u by do beta into do beta by do eta. And here you can see that this will be do eta if you remove u, and do alpha by do eta is 1. So, you have do u by do alpha, and here minus, because do beta by do eta is, because beta is this, this is minus 1. So, you have do u by do beta. So, you remove this u both sides, you have this transformation do eta and do xi. So, you come back and put it here. So, if you do that, so what you get is u xi eta becomes, so you can replace do xi with do alpha plus do beta into, so do alpha minus do beta on u. So, this becomes nothing but do square u by do alpha square minus do square u by do beta square. Okay. So, go back into the new variables. Okay. So, this is what you have. So, your canonical forms, this is now your equation, your equation is this now. So, this in terms of new variables u xi eta becomes this one. So, you have u alpha alpha minus u beta beta equal to lower order terms, lower order terms. Lower order terms here means in terms of u alpha, u beta, u of alpha beta, this is what is it, okay, functions of alpha beta. So, this is another canonical form for hyperbolic. This is the hyperbolic canonical form. So, when xi and eta are real valued functions, so either this is one canonical form for hyperbolic or this one is another hyperbolic canonical form. This looks like a wave equation. If you assume that all the lower order terms are 0 or not there, what you get is u alpha alpha equal to u beta beta. Okay. So, this is a kind of wave equation. So, if you replace with alpha alpha as tt, a time variable, and this is a spatial variable beta beta. So, what you have is this minus this equal to 0. Okay. This is a wave equation. Wave equation. So, if you actually include the speed c square, okay, if you put a c square here, so you have c is the speed of the wave, c is the speed of the wave, okay, wave speed of the wave speed, okay, you can write wave speed. So, it is a constant c square. So, this is a wave equation. So, this is similar to this canonical form is similar to the wave equation. So, whatever characteristics of the wave equation if you look at it, if you consider string if you consider that satisfy the wave equation. So, you can see that waves propagate with a finite speed of propagation and you have certain characteristics. It has only two kinds of characteristics along which this PDE becomes a ODE, okay, that is what is it is a constant. So, along that along those curves, if your PDE acts as it becomes a ODE, then you say it is a characteristic curve. Okay, those curves are nothing but what you get is these new variables alpha and beta act as those characteristic curves. Okay, the transformation what you get from xy to xi and eta are a characteristic curves. Along those curves, your equation, your partial differential equation becomes simpler equation. So, that is what along those curves you call. So, because it becomes simpler means from partial differential equation to you expect it to be some simpler form, that is ordinary differential equation which you can solve. So, characteristics of this wave equation, solutions of wave equation are it has a finite speed of propagation. If you look at the wave parabolic equation, for example, that we see when discriminant is 0 and you have this one, in this case is a similar equation will be heat equation where heat propagates at infinite speed. Okay, you cannot have a finite speed of propagation. In no time, if you give initial values which are disconnect, okay, suppose you give certain temperature at in a rod, 0 temperature at one place and 100 degree temperature at another part of the rod, in no time it will be uniform. So, what happens when you give 0 degree centigrade in part of the rod and some other non-zero heat at another part of the bar, and you see that clearly it is a discontinuous function, 0 at one place and say 100 is at one place. In no time heat diffuses, okay, the temperature will be distributed in no time, diffuses in no time, heat diffuses into no time, and in few seconds you see that it is a smooth curve from 0 to 100. It is a discontinuous function. Now simply you will get a continuous curve. So, this is a different from wave equation. So, you see that you have infinite speed of propagation, as if you see as a wave solution as a wave, the speed will be infinite here. So, it has a different characteristics, heat equation has a different characteristics. That is why we categorized these kind of equations as a parabolic based on the so analogous to the conic sections for the quadratic equation. So, in the same way here we have right now we have this hyperbolic equation, and xi and eta when you transform into u xi eta plus lower order terms, that canonical form you can convert into new canonical form. This is a second canonical form, that is hyperbolic, where you get this looks like a wave equation. So, this is wave equation, this is a hyperbolic. So, what happens if when the discriminant is non-zero, what if you have xi and eta, or if xi and eta are complex functions. If they are complex functions, you do the same thing. Alpha is if you take the sum of that xi plus eta, and beta is xi minus eta by 2i, you take here 2, then it becomes, this is simply real part of what is alpha then. If you take like this, if xi and eta are complex functions, first of all xi equal to eta bar, right. So how did you get your xi and eta? Basically when you have the discriminant is non-zero, these are the two differential equations where a, b, c are real valued functions. When you take this bar, okay, this gives you xi and this gives you a solution. Y of x is whatever you integrate, that will be xi of x here, this is eta of x here. So when these are functions, when these are what you get is if, because b square minus 4ac when it is negative, I comes here, okay, you have I comes here. So you have I here minus I here. So if you whatever you integrate this equation and take the bar, that is nothing but you get this one, or you simply take the bar here, this is nothing but this ODE, or you take bar here, that will become this ODE. So what you see is that after integration, xi is nothing but eta bar, or eta is nothing but xi bar. So you see that when they are complex valued functions, they are nothing but they are just conjugate to each other. So they are complex conjugates, they are the two transformations. Now what you do is when you take this sum and difference as the new variables alpha beta, alpha is nothing but real part of xi, beta is nothing but imaginary part of xi. So with these new variables what happens, you can use the same technique, u xi eta becomes, so you see that this becomes do xi b, and now you have alpha is different. So alpha is this one, and what you have is u do xi is u xi is u alpha do alpha by do xi, that is half, plus u beta do beta by do xi, that is 1 by 2y. Okay. Similarly u eta is u alpha do eta by do alpha by do eta, so that is half, minus u beta do beta by do eta is minus 1 by 2y, minus I already have here 1 by 2y. So this is what you get. So this gives me do xi is half do alpha plus or minus I do beta. So when you take this bring this I up, it will become minus I. So similarly you get do eta is from this second equation, you have 1 by 2 is common, so you have do alpha minus I, when I bring this I up, so it will become plus I do beta. So this is how your do xi and do beta becomes. Now if you put it at u alpha beta, what happens to your u xi eta? U xi eta plus lower order terms becomes equal to 0, becomes in terms of these new variables alpha beta as alpha do alpha minus do beta into half 1 by 4 and do alpha plus I do beta u plus lower order terms equal to 0. See here lower order term means it is u alpha, u beta, and u is a function of alpha beta. So what happens to this term? This term is nothing but now u alpha alpha plus u beta beta. Of course 4 you can bring it this side, and 4 into lower order terms, again lower order terms equal to 0. So this is what, this is a canonical form for when xi and eta are second canonical form when alpha beta when beta b square minus 4ac is non-zero. When b square minus 4ac is non-zero, you get a second canonical form by the new transformation here. Okay. So when xi and eta are complex functions, you do this transformation to see that this is a elliptic equation. Okay, this is the canonical form which is equivalent to elliptic, because if you ignore the lower order terms, this looks like alpha beta u alpha 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 alpha, you can take it as xx plus u beta beta as your yy equal to 0. This is a Laplace equation. Laplace equation. So both x and y are belongs to full R, R2. Okay. So you see that So, this satisfies the Laplace equation, it is a different thing. So, you do not have time here, only spatial variables. This is actually steady state condition when you have a plate is having with a heated plate, and initially at some heat, after diffusion, after some time it reaches the steady state. What you see is the heat distribution. Heat is at the steady state. Of course, you have some boundary of the plate is assume that you fixed it, you say insulated. So, what happens is whatever initially what you have at some point, it may be high temperature to lower temperature, it reaches some steady state, that is the distribution. Those are solutions of these equations are steady state condition for the heat equation. So, that is what you see. Okay. So, this is a different you do not have characteristics here. So, this is a different thing. So, you do not have time variable here, this is actually you purely boundary data you have to provide for this Laplace equation. So, the canonical form of your second order linear partial differential equation, when it becomes this type, elliptic type, that means the characteristics of such equation are basically you have to provide the only boundary data for such an equation, so that the problem is well defined. And if you have hyperbolic equation, you have to give initial data because it looks like a wave equation. So, because it has a two time variables, okay, t is positive and x belongs to r. So, because time t you have, because the second order time derivative second order, you have to provide two initial data at u at t equal to 0, and the derivative dou u by dou t velocity if you think of dou u by dou t at t equal to 0, that also you have to provide as initial data, and because if you whatever boundary data you can provide. Okay. So, if these are if xi and eta are real and complex valued functions, when you get these from this ODEs, what you get is one of these canonical forms. So, either hyperbolic equation, that is like a wave equation as an example, or elliptic equation as if these are complex valued functions. Okay. When you have elliptic equation, it looks like when you do not have lower order terms, it becomes a Laplace equation. So, it is basically purely you do not have time involved here. So, these are purely different equations. So, it is boundary value problems only you can define, because you can only give when you have a boundary like this for the Laplace equation, you should provide the boundary data. There is no t, so only x, y are spatial variables is a two dimensional Laplace equation. Okay. So, this is what is the case when discriminant b square minus 4ac is non-zero. So, either case you can see that either it becomes one of these equations, one of hyperbolic or elliptic equation, okay, by transforming one more time from xi eta to some alpha beta variables, which alpha beta you take it as simply sum and difference between difference of these functions xi and eta. So, what happens to when b square minus 4ac equal to 0? If b square minus 4ac equal to 0, in the earlier video we have shown that you could get only xi, and eta you have to choose in such a way that Jacobian is non-zero, and then b star square minus 4ac star is 0. That makes it because you have to choose c star is non-zero. If you choose c star equal to 0, then the Jacobian will be 0. So, that is contradiction to the assumption that Jacobian is chosen in such a way is non-zero by choosing a suitable eta function. So, that makes it c star non-zero, and that but a star is 0 with which you got the xi function. So, b star has to be 0. So, that means finally you end up c star which is non-zero, that is u eta eta plus lower order terms equal to 0. So, when we will continue from there. So, what happens if b square minus 4ac equal to 0, what you end up is the canonical form is u eta eta plus, because c star is non-zero, you can plus lower order terms equal to 0. So, this is the canonical form of parabolic. This is the parabolic equation. So, if your equation transforms into this type, only one variable u xi plus lower order terms or u eta eta plus lower order terms, then you say that it is a parabolic type of equation. Okay. So, we will see. So, what is the example here? So, in this case, so example we have not talked about the example. So, here the typical example is heat equation. So, what is the heat equation? So, heat heat equation is the temperature distribution, so which is the time derivative. So, you have a time involved here, u is a function of x and t, x is the spatial variable. So, basically x is, if you consider a rod of finite length or infinite length. So, this is the one dimensional. So, x is only spatial variable. So, in this, what is the temperature distribution? So, that satisfies this equation ut, the time derivative of the temperature distribution x of t, okay. A temperature at every point at every time t. So, this is ut equal to some constant, actually this is a constant kappa, that is a specific heat constant into uxx. So, x is because I choose this infinite rod, then it is full R. If it is only finite rod, you have to, suppose you take only finite rod, then you have to take A to B, and then you have to have, so this is the boundary, these are the boundary points, and initially, so because the t is the time derivative and which is only one derivative. So, you have at t equal to 0, you have to provide a boundary condition, initial condition. So, u at x and t is 0. So, this you have to provide some function of x, this is the initial condition, okay, initial data. Initially, what is the temperature of this rod at t equal to 0? Then what happens if it satisfies this equation? If you, what the solution actually gives you what is the temperature distribution for all times, all along the rod. If it is a boundary, so you should also know exactly initially what is the R boundary data for all times. You should provide a boundary data because it has a two derivatives. You have to provide two, you have obviously two boundary points. So, you should provide data here. So, you have boundary data. Boundary data is u at A, if A is the boundary, at t, this is some f1 of t, and then u at B at t, this is another some function of t. So, these are given. If you know that this initial and boundary data are given, you can also choose. So, physically, if you say I insulate at these endpoints, I can make it 0, or temperature, you maintain 0 temperature at here and here, this is 0, okay. And you can also say that physically you can you insulate these ends. Initially, you have some temperature of a rod, and with the rods are insulated under some assumption that assume that a rod is uniform and a temperature heat is going only in one direction. All along this lateral sides, heat is not dissipating. So, that means it is insulated all along the rod, okay. So, that heat is dissipating only in one direction, or only all along the x axis only. So, under those assumptions, if you say that insulated boundary condition will be simply the derivative, flux has to be 0, that means nothing is going out. So, that is the derivative. So, that is dou ux at B both are 0. So, these are insulating boundary conditions. If you remove this x and x only u is 0 at both the endpoints, that means you are maintaining the rod at the temperature 0 or some constant, okay. You can give some temperature T1 or T2, this is the temperature T1 and T2 at the endpoints, or you can provide flux boundary condition, 0 flux boundary, that is insulating rod, that is ux at AT is 0 and ux at BT is also 0. So, that means a rod is insulated. So, these are also this, either this or this you can give boundary data. So, this is like this equation. So, you see that uxx is plus lower order terms equal to 0. So, that is why this is a parabolic equation. Most of the so any linear partial differential equation of second order, you convert it into some new variables xi and eta, okay. Once it takes either u xi eta equal to plus lower order terms equal to 0, then it is either hyperbolic or elliptic. As a sub case, you can also see that if depending on what is your xi and eta, if xi and eta are real valued functions, again you use the new variables alpha and beta as sum and difference, and you can convert u alpha alpha minus u beta beta equal to 0. So, that is a kind of hyperbolicity when you see minus, and if they are complex valued, then it becomes u alpha alpha. Xi and eta are complex valued functions. again you can use the transformation some alpha beta, alpha as the sum of xi and eta by 2 and beta is xi minus beta divided by 2i. So if you take that, you see that it will become u alpha alpha plus u beta beta is 0, that is Laplace equation type, plus lower order terms equal to 0, that is elliptic equation like a Laplace equation. And if you see only two same derivatives, second order derivative plus lower order terms either xi or eta, so that is a parabolic equation, that is looks like a heat equation, typical equation, a heat equation. So this is how you reduce linear second order partial differential equation of second order, you reduce to another second order linear equation in new variables xi and eta. Okay. This is not really new what we have done for the PDEs, we have already done similar thing for the ODE. See what we have done for the second order linear ordinary differential equation, we reduced it to normal form, that means we take a sum transformation. So from this we took some transformation, with the transformation we removed the first order derivative. So that is reducing the equation of second order equation, second order ordinary differential equation into a second order differential equation without first order derivative in it. So that is putting in the normal form or standard form, with which if you see that the reduced equation is actually with any transformation if you choose, then it will become again second order equation with the first order term also will be there. But if you choose in a specific way the transformation, you can choose that transformation such a way that first order term you can make sure that it is removed, it is 0, coefficient is 0, that fixes the transformation. So once you know that, so you have a reduced equation is second order without first order derivative in it, then you can expect to solve if it is in a simpler form. So we do the same thing here. So that is what we have done here. So here even for partial differential equations of second order, linear partial differential equation of second order, we have transformed from xy to xi and eta. Xi and eta are functions of xy to these new variables xi and eta, then it becomes second order linear partial differential equation in new variables xi and eta. So this does not mean that you can solve this one. Okay. So you fix this xi and eta in such a way that A star and C star are equal to 0. So by choosing that, you reduce that equation into a simpler form. That simpler form is either hyperbolic, or that is what you are simply calling either hyperbolic, elliptic or parabolic type. Okay. Simpler form is u xi eta plus lower order terms 0, or u xi xi or u eta eta plus lower order terms are 0, one of them. So either mixed derivatives or only should be there, or only two derivatives of one variable, other variables are not only lower order terms it will be there. So these are canonical forms. So this is like putting in the standard form. So the standard form is in a nice form, then you can solve it, you can expect to solve it like in the ordinary differential equations. Here also if these canonical forms are one of these equations, heat equation, wave equation, Laplace equation, you can solve it, or otherwise also if it is in a simpler form, so we can simply integrate by elementary methods, you can integrate some of the equations. So first we will see, so in the next video we will try to see how to reduce, how to actually demonstrate with an example. I will demonstrate with an example in the next video by reducing given second order linear partial differential equation into a canonical form, and then we will try to solve if it is possible. Okay. So we will see that in the next video. Thank you very much.